Okay, so yes, so thank you for inviting me. I am Tommaso Chiarotti. I'm a PhD student here in the group of Nicola Mazzari. So this work has been done in collaboration also with Andrea Ferretti, who is at CNR in Modena. Okay, so what we are going to discuss here is the new development of what we are working on for some time, which is in some sense it treats electron interactions, and it aims to get energy and spectra from the formalism. I will explain what I mean by this. Okay, so this is the motivation slide, to be clear. So oh, sorry, I didn't put. I just see that I didn't put the reference of the Lucia Reining paper of Zhu and the PNAS paper. But so this is a very well done, let's say, comparison between theory and experiments. Theory is GW plus cumulant. We will not touch this thing in this talk, but let's say, so this is the spectral function of aluminum. The left-hand side is the hardness experiment. The right-hand side is the prediction. They do agree pretty well. I think that everyone can agree on this. Now, there are two problems with this picture, at least two issues, let's say. So one issue is, okay, so you got a very good spectral function. What about the total energy, for example? What about the thermodynamics of this calculation? The other issue is what about correlated materials? Okay. So there are already answers of this, of course, in the literature, vast 40 years of research about this. But let's say we are gonna overview a bit the literature, and then we're gonna, let's say, address what we thought. Okay, so the open issue, as I said, is getting both the spectra and the thermodynamic quantities together from a single calculation, from a single formalism, exactly as you do, for example, in a DFT calculation. You get the spectrum, which is the connection spectrum, and you get the total energy. Okay, you want to do the same. Second thing is the fact that for sure this has to come from dynamical frequency-dependent potentials. Now, there is a motivation on this in the next slide, but I mean, anyone that is familiar with the framework knows that frequency has to be there to predict correctly the spectrum. And then to get the total energy, you need the function. Okay, so this is exactly what we worked out, let's say. So we actually propose some of our post representation to treat the dynamical potentials, which means that to implement the frequency in a computer code, of course you can do it point by point, frequency by frequency, but maybe it is better to have a basis for frequency for this, for the propagators, let's say. Then we see that actually this leads to the algorithmic inversion method, which in some sense aims to map a interacting system, sorry, to a non-interacting one exactly, and that shares the same Green's function. So not the ground state density as connection DFT, but that shares the one particle Green's function, and we will see how to do this. It's actually impossible to do this if you stay in the same Hilbert space, but we see that if we enlarge the Hilbert space, augmenting the degrees of freedom, this is actually possible. And then we're going to design a new functional, a novel functional, or at least a novel approximation to the Klein functional, which comes from the localized-GW, which I'm going to explain what it is, comes from the localized-GW approach, and in some sense generalizes DFT+U. So we have called this dynamical advanced functional. Okay. Okay, so this is why. So maybe this slide is not very useful for the community since everyone knows this. But let's say for why dynamical potential are needed to predict accurately the spectrum for a material. Well, the simple reason is because frequency comes from an embedding approach. I have a slide on this later on, but so for sure, so let's say, so this is so if you do an embedding, it means that let's say that you want to restrict your degrees of freedom, and indeed the cost of this is exactly dynamical potentials. Now, for dynamical potential, they can be non-local potential, and many-body perturbation theory is all about this, GW and T-matrix, all of this. Then there are also local formulations. I put the citation here for DFT, but it's the same level as many-body perturbation theory, so everyone knows what it is, let's say. Then there are interesting work on the dynamical Shamshluter of Gatti, etc. Ferretti did some work on dynamical Shamshluter versus Koopmans, and then there is the new connectors approach of Lucia Rein, Marco Vanzini, and all of this. But so this is all to say that all of these treatment, they actually aim to get a good spectral function using a dynamical potential. And so indeed, in some sense, we are moving along this arrow, let's say, to get a good spectral function. So this is an overview of the entire electronic structure, let's say. So this is taken from the Marzari paper of Nature paper of 2021. So indeed, the electronic structure is about getting the wave function. So maybe reduced density matrix theory can be of help. Getting a good ground state density or doing ground state quantities, also time dependent, DFT. But also it can be about getting good spectral functions. And so indeed, GW is at this level, dynamical Mifid theory is at this level, and local formulations, let's say, aim to get a good spectral density of the system. Okay, so now we have justified, let's say, why we need dynamical potential to get good spectral quantities, but it's interesting to know that actually with dynamical potential, also the thermodynamics of a calculation can be calculated. With the thermodynamics, I mean all frequency-dependent quantities, which are total energies, number of particles, bulk modulus, forces, all of this. So this is the Calypso-Migdal formula, to be clear. Okay, so and we actually know that to get this potential, we need to perform some operations in the computer codes, let's say, which are, for example, convolution in the case of GW. Okay, so how to perform this operation, let's say, efficiently? Well, we have worked out that actually if you write the sum over poles representation, which is this thing that we introduced, let's say, of the propagator, and then all of these integrals are actually analytic. You just use the Cauchy residue theorem for this. So in this talk, I'm going to refer this as the poles of the Green's function, of course, and the I as the residues. Now, this is actually not new. It's actually a truncated lemma representation, and actually Behnam Farid already in 1998 of course, thought about this and what does it mean with respect to continuous fraction formalism and all of this. What does it mean to have this form? Okay, but so the idea is, let's say indeed, so if you have a frequency-dependent propagator, so this is, right, but this is the homogeneous electron gas at the G0W0 level for two densities, spectral functions or Green's functions, the spectral function is just the imaginary part, looks like this, looks like a pole structure. So you get, ideally, you put a pole there, you put a pole there, you sum, and you get, let's say, this function, a good approximation for this function. And then with this form, you actually can get the integrals, as I said, the convolutions, and the frequency integrated quantities. And this is, for example, exactly the K-resolved the frequency integrated total energy for the homogeneous electron gas. Okay. Now, so as I said, this allows for the full frequency treatment of propagators, and using the Cauchy residue theorem, you can get all the quantities that the electronic structure is interested to. Now, we will see that actually very interesting, this is a very unexpected properties. This actually allows to solve analytically the Dyson equation. There is an entire part of the talk about this. Okay. So, so this is just to say, how do we actually get these coefficients? We have actually designed two strategies in two different papers, let's say. So one strategy is about looking at the spectral function and perform a non-negative square fitting. So supposing that we actually have this function in frequency, we actually want to get, let's say, the estimation for the amplitudes and for the poles of the propagator. Okay, we look at the spectral function. We find the IE by performing simply this minimization in which this quantity is known. These quantities are actually, this is a basis. So in some sense, we are just expanding on this basis. This n here is to actually, this function, we call it nth order Lorentzians, because if n is equal to 1 is actually Lorentzian, but if n is more than 1, let's say this is a generalized form of a Lorentzian, which actually it helps to do the integrals, because a Lorentzian, actually the Gaussian formula would diverge if you actually use a Lorentzian. So instead, if you have a not fat-tailed function, it's better. The point is that from this, you can actually get the SOP representation from the propagator. So the poles you do have to adjust the combination of epsilon I and delta I, and the I you do have from the minimization. And you can find the details of the paper of how this works for, let's say, a peaked function, which we use the Gaussian. Okay. Now, the second strategy is instead in the new paper, let's say, in which one DX defines the poles and the amplitudes of the propagation by simply minimizing this. So because this is the denomination, this is a nonlinear algorithm, a non-linear least square algorithm can be done. But let's say that the juice of the fact is that it's exactly the same. So you get the poles after the minimization, you get the poles and the amplitudes of the propagator if, sorry, this should be a U, if the screen potential is known. And indeed, we have performed this. I will talk about what it is this, but let's say, so this is a real case example on Strontium validate, in which this is the screen interaction, which I will explain what the average screen interaction on the Hubbard manifold. And so the black line is the calculation on grid, and the green line is just the approximation when the SOP form has been got. Okay, so this is just a recap. So this is so the dynamical quantities are difficult to treat for the analytic structure, for the pole-like structure, as I said. Didn't mention actually that I should have mentioned that there are other ways to treat this. In some sense, the imaginary axis formalism is one of those. There are issues with that, not from the integral point of view, but from the when you try to get the spectroscopic quantities, because you need to do an analytic continuation, which is difficult to do numerically, but this already has been, let's say, tackled in the past in that way, for example. Now, the sum of a representation is our method to solve the problem. And once it is known, the analytic moments, convolution are all available. And also, as I said, very interesting, the Dyson equation can be obtained. And let's say the next part of the talk is about this. So the point, sorry that this is a bit a large gap of what I've been talking before, but I think it is very interesting to understand that the Dyson equation is a nonlinear eigenvalue equation. And is actually the generalization of the Schrödinger equation for embedded open problems. Now, how to see this? We will see this in detail. This is just a hint. So the point is how to get to the Dyson equation. And say this is, for example, in the books. And so you start with the Schrödinger equation, and then you focus on 1 degree of freedom. The embodied Schrödinger equation, which has for n particles n degrees of freedom. You focus on just one. Particles are indistinguishable, so it doesn't matter which one. Now you focus on just one, and you write this equation by simply dividing this problem in as an embedding problem. So with the 1 particle Green's function here, the n-1 particle Green's function, let's say coupled as a buffer, let's say, and a coupling. Perfect. Now you can do this for the Green's function. You can do this for the Hamiltonian. Now the idea is that this is actually this equation written. The point is that if you use the second equation into the first, you actually end up with something like this. You call this the self-energy, and you get from the n particle problem to a one particle problem. Now this is similar to what happens with symmetries. You use group theory to end up with few degrees of freedom. But the point is here, there is no symmetry. So you cannot do this without losing something else. And what you lose actually is the linearity of the Schrödinger problem. And indeed, this is a nonlinear eigenvalue problem. As I said, we'll see this in a moment. Okay. Now, this is the comparison indeed between non-interacting problem and an interacting problem. Okay, so in a non-interacting problem, you can do that mapping, but a self-energy doesn't come up because the Hamiltonian is simply the sum of the n particle Hamiltonians. So if you restrict to one degrees of freedom, only H0s come up. And you diagonalize to solve this. So this is the Schrödinger equation for a non-interacting system. And to solve it, you diagonalize the problem. It's a linear problem. You get eigenvalues and eigenvectors. And very interestingly, let's say, you get a sum over poles form of the Green's function. So you see the residues are here, the poles are here. And these are just the eigenvectors, and these are just eigenvalues. Now, when instead you have an interacting problem, you have a self-energy. And it's very clear that this equation, since these operators depends on the eigenvalue, should be, let's say, evident that this is a nonlinear problem, because indeed the nonlinearity is the mapping of the operator on the eigenvalue itself. And this is actually very well studied in mathematics. And it's called the nonlinear eigenvalue problem when operators depend on their eigenvalue itself. Now, interestingly again, the solution of, if you are able to solve the equation, the nonlinear eigenvectors are the amplitudes of the Dyson inverted propagator, which is the Green's function here, and the nonlinear eigenvalues are the poles. So the point is, since in Green's function formalism, we need the dynamical potentials, how to solve the Dyson equation. Cannot be, diagonalization cannot help, because this is not an eigenvalue equation. But mathematicians have worked out, let's say, that if the self-energy is a polynomial, the solution, which are the nonlinear eigenvectors and nonlinear eigenvalue, is actually can be computed. The problem is that in material science, for real materials, the self-energy is hardly a polynomial. So this is the imaginary part and the real part of the self-energy on the Strontium-Weyl, on the T2G manifold. We'll see about this at the end of the talk. But the point is that the dynamical potential here, the self-energy, is hardly a polynomial, as I said. It actually resembles much more a sum over poles form, because indeed, looking at the imaginary part, this is just the sum of the peaks, right? Okay. So maybe one is lucky enough that if the self-energy is of sum over poles, so we treat just the one pole case in this slide. So if the self-energy is composed by just one poles, we can actually solve the Dyson equation, and this is actually true. And it is very simple to show, actually. So if the self-energy is of this form, you can just rewrite gamma as doing the square root of the singular value decomposition. And this problem, you already know how to solve, because this is exactly this problem, in which we have embedded down by performing by writing the second equation into the first one. And now we just need to embed up. So going in this direction and write the total Hamiltonian for this system with augmented fictitious degrees of freedom. And the Green's function, which is the Gn here, is known. And the G, the one particle Green's function, can be simply get by the projection on the H0 Hilbert space. So indeed, as I said, if the self-energy is a sum over poles, you can actually get the Green's function as a sum over poles. Now, okay, so we did this for one pole. We can do this for a sum over poles with just the augmented, so the fictitious non-interacting system that you need to get, that you need to diagonalize. It has just the residues instead of one residues, you and the residues instead of one pulse, you get 10 poles. But the point is that you build this H effective Hamiltonian, you diagonalize it, and by a projection, you get exactly the Green's function of the problem. Now, okay, so this is a bit of a recap, which I think that I'm short of time, so it's better that I go, yes, faster in the recap. Now, the point is that the Dyson equation is the nonlinear generalization of the Schrödinger equation for embedded open systems. And the point is not the generalization. The point is the nonlinear part, of course. Now, the algorithmic inversion method exactly maps the interacting system into a non-interacting system with augmented degrees of freedom, which are the poles, if you want, and the residues doing the coupling of the self-energy, and shares this fictitious non-interacting system the same one particle Green's function as of the interacting system once the spurious degrees of freedom are traced away. So the idea is that if we represent the self-energy as a sum over poles and we diagonalize this, we can actually get the solution of the Dyson equation. Now, I didn't write this again, but this method is actually very similar to Kotler 2004, yes, Summers of Kotler 2004, Aule also, in which they actually used a very similar method, let's say, to get the solution of the Dyson equation. Now, there are differences, of course, between the two methods. The point is that, let's say that they used it just to solve the Dyson equation, not to get the sum over poles form of the Green's function. But let's say that in the literature, this thing was already there in some sense, just a bit, maybe not totally clear, let's say, from my point of view. Okay, but anyway, so the point is that we used this formalism to calculate, say, accurate spectral function and correlation energies for the electron gas, and you can find all the details in this paper. Okay, so now, and we did this in the GW approximation, G0W0 calculation for those. So that was the GW approximation for the self-energy. Now, the point is that, okay, so we have shown that dynamical potential are needed. The sum over poles representation can help you to do the integrals, and the algorithmic inversion method can help you to find the exact solution of the Dyson equation. Now, but what about the functional form of the self-energy? So how the self-energy looks like? Okay, and so indeed, from all the literature, we know that if the self-energy comes from a functional, which can be a Luttinger-Ward functional or a Klein functional, the self-energy will preserve some quantities which are very important for electron structure, which is the angular momentum, the number of particles, all of this. So what we want to do is to design a new functional for correlated systems. Why? Because well, GW is a very good functional, let's say, but for correlated systems, it has some issues, let's say, and also it's doing implementation of GW, calculate the total energy, and all of this is very difficult. So maybe a simplified functional also can also help. Now, so this is just the comparison between to introduce the Klein functional. So it's just the same as in density functional theory. You want a functional of the ground state density. In density functional theory, you want a functional of the Green's function. by doing the derivative with respect to the density, you get V d Konesham. By doing the derivative with respect to G, you get the self-energy. And the function can be partitioned in known parts and unknown parts, and exactly as for Konesham DFT, the same as for the Klein function, in which the phi part of the functional is not really known. Now, this is actually a bit of a simplification of the writing of the Klein function, because in solids, these terms diverges. But let's say that we have regularized the expression. We used another expression which is a bit complicated, but more complicated. But the exchangeal part is the same, which means that we need to approximate the exchange correlation part of the functional, the exchange correlation in this case, to get a closed form for which to do the derivatives and to do the calculation for the material. Now, sorry. Now, so the idea was to design a localized GW functional. To be clear, this is the localized GW0 function, to be clear. But in any case, so the idea is that well, how do you design a function? You just write it down, and then you see what you get. Now, if you write down this function here, which you see is a function, not really of the Green's function, but of the projection of the Green's function on a localized Hubbard manifold. So suppose that your material, you know that there are D bands or F bands, or D orbital or F orbital that contributes along the, let's say, the energy surface, around the energy surface to the electronic structure of the material, and you know that actually this defines, as in DFT+U, a Hubbard manifold, which means that you can project onto this Hubbard manifold, and indeed, so this functional is not a function of the entire Green's function, but is a function of the projection of the Green's function onto the localized Hubbard manifold. So this is just the strontium 1 and the orbitals. How do they look like? So you project indeed in this space the Green's function. You write down this functional, and if you do the derivative, well, it's very simple to see that you can actually get this form. Now, this is not new. This comes from a localized version of GW, rewritten a bit. So if you look at this paper, which is from Ariaseta one, so it's not written exactly like this, but it can be written. Let's say I put the wrong reference. Sorry. If you look at the archive paper, I will refer to this in the end. But if you look at the archive paper, the supplementary material is very simple to get. Let's say to pass from the form of the Fermi form to this one. But the point is that you get a localized GW self-energy. Now, this localized GW self-energy is a good approximation to treat correlated materials, as we see. Now, there is an issue with this, which is the double counting. So if you want to correct a DFT function, so if you want to use this new function as let's say corrective term for DFT, which actually gets you more than DFT, because other than correcting it also gets you the spectral, all the spectroscopic of the materials, not just the bands, all the spectral function. But if you want to let's say use it, you need to have a double counting term, because in the DFT functional, the interaction on the Hubbard manifold are already counted, are already taken into account. So if we want to treat them at a different level, which we are with the localized GW functional, we need to subtract, let's say, the DFT interactions, so the DFT contribution to the interaction. And so then you do this by this double counting term. Now, this double counting term looks ugly, if you want, but it actually traces back exactly to the double counting term of DFT+U in the fully localized limit. So indeed, so to write this double counting term, it's not complex. You just take the double counting term of DFT+U in the fully localized limit form. Okay, So now that we have a functional, the total energy of your electronic structure calculation will look exactly like this, with the Klein function and the approximation to the phi functional. And that depends on the projection of the Green's function onto the Hubbard manifold. Now, interestingly, if why do I write generalizes plus 2? If U is frequency independent, so U is equal to U0, this term is exactly this one, if you do the integrals. And so this is actually very desirable, because we know that DFT+U is very good for ground state quantities in correlated materials. Of course, not strongly correlated. It's more complex situation, but in correlated materials, DFT+U works fine. So indeed, so this is let's say in some sense is a generalization of DFT+U functional with a dynamical formalism. Now, so this is sorry, this is a bit a repetition of the slide. The point here is that the fact that indeed, as I said, the function that we need to take into account is exactly this. Is the DFT+U function, is yes, the localized-GW self-energy, and is actually rotational invariant, exactly as in the two-direct form, which is this one, of the DFT+U self-energy. Okay, so let me see how am I doing with the time. I'm already over. Okay, perfect. So we move to the results very quickly. So sorry for the references, but indeed in the archive paper you find all the references correctly. Let's say. So the point is that okay, so you have all the formalism to perform electronic structure calculation with a new formalism, a new function, everything. So you just need to implement it and see how it goes. We know, so I knew already that in the strontium vanadio, which is not a simple material to treat, maybe doesn't require DMFT, but it's for sugar correlated metal. Now, indeed, so you have the formalism, you have a closed form for the total energy, a closed form for the self energy is all written in sum over poles actually, and so indeed you can use all this machinery. So the self energy comes as a sum over poles form if you have the if you start from a Kohn-Sham-Green's function, so you can use the algorithmic inversion method to get the exact solution of the Geiger equation to get the Green's function. You get the Green's function on sum over poles by this. You look at the spectral function, it looks very good in comparison to, let's say, experiments, more advanced treatments, and so on. But also, indeed, so what does it add, all of this does it add to the thing, is the fact that since you have a subform, you can actually perform all the integrals to get the Greek modulus, the phonons, the forces, if you want. Now, there is an issue actually, and indeed you see that actually this curve here, which is this work, which is calculated with this local dynamical Hubbard functional, the fact that the equilibrium parameter is not correct. And the issue is exactly self-consistency. So those are not self-consistent calculations. And indeed, the zone center phonons have not been calculated with the dynamical, with the Hellman-Feynman theorem, but simply moving the atoms and performing the differences. So these results have to be taken as cum grano salis, let's say, exactly as you do G0W0 results, same level. Okay, but and this brings me exactly to the conclusions. So this so I hope that I showed, let's say, that frequency is tough, let's say, tough argument to deal with. Let's say it brings non-linearity into the whole quantum mechanics, let's say, from embedding. Now the algorithmic inversion method helps you to solve the Dyson equation. So in some sense, that all of the formalism on the sum over poles formally helps you to deal with this frequency. In some sense, also linearizing, as a mathematician would say, which doesn't mean from a perturbation theory point of view, but from an exact point of view, linearizing all the formalism, let's say. So providing a linear framework to work with. Now, given the self-energy on SOAP, the exact solution of the Dyson equation is known, the Green's function, the Dyson orbitals are known, the excitation energies are known. Now, this has been the first paper that we published on this, on the homogeneous electron gas. And now we have actually a paper on real materials, which is we took transient validate, but we could took any gapped correlated and gapped correlated metal or insulator is the same. Okay, the filters perspective, as I said, is do some consistent calculations, and of course is other applications of the algorithmic inversion method, which are a work in progress. Okay, thank you very much. Sorry that I took too long.
Thank you very much, Tommaso. No, I think you're almost perfect on time.
Okay, thank you.
Anyway, we're not too strict. So thank you very much. So are there any questions? So if you have questions, go to the reactions part and raise your hand. So maybe I can start. So if I understood correctly, so in the second part of your presentation,
Yeah.
where you introduced the algorithmic inversion method, it was more of a proof of principle because you used the GW self-energy.
So this thing, the application, we used the GW self-energy to do the actual calculation. So this is a proof of principle, correct? Now so with the algorithmic inversion method, now the self-energy can come from any, say, function of the Green's function. Can be GW, can be localized-GW, can be matrix, can be whatever. The point is the fact that if you represent it as a sum of poles, you get, let's say, the solution of the Dyson equation for instance, but via diagonalizing a matrix, let's say. But yes, so this is the point.
Okay, and then in the second part, you try to find a better self-energy, and you use this localized W.
So I mean, correct. So better self-energy, I wouldn't say that doing better than GW is also not impossible, but let's say so localized GW was already there in the literature, and I already knew that on transient validate this was working really well. Now the point is that in this part we functionalize the theory, so we provide for a functional of that gets you the self-energy as the localized GW self-energy as derivatives, and we use it to calculate indeed the self-energy was already there. You calculate the spectrum, but then with the function you can actually get the frequency integrated quantities, so the total energy, the derivatives of the total energy, and all of this.
And what do you take for U?
Sorry?
What do you do?
Correct.
That was actually my question.
Fantastic. So sorry, I didn't speak about this. Let me find the slide. So I actually thought that the slide was there, but thank God it wasn't, because maybe it was already too long, the talk. So this is what we take for you. So the since it comes from a localized GW point of view, this functional, you can hint, let's say you can guess that a good guess for you is the RPA U. So U is calculated in an RPA, doing the RPA calculation for the screen potential. Then you average this quantity over the localized manifold, and you get U as a simple function of frequency. Now this is resonant with what Rinke did in his paper in 2010 to actually get DFT+U from GW. So to get that, they said, okay, we do static GW, so convex if you want, then we localize it, we define U exactly in this way, we get DFT+U. Now this is parallel, let's say. You don't do static, so you leave GW to be dynamical, so frequency dependent, but you do all the rest. You localize it, you average it, and then you get the U of omega, and you use it in this functional formulation indeed.
Okay, thanks. There was the question by Raffaele.
Hi, Tommaso.
Hi, Professor.
Sorry, I have to take off my, otherwise I have an echo. Do you listen correctly to me? You get?
Yeah.
Okay.
Perfect.
Now, is your approximation exactly number conserving? That is, if you sum all of the residues on the poles, do you get exactly the number of electrons per cell, or only approximately?
Correct. So, I answered this question in the two different parts of the talk, let's say. So, if you have a self energy,
yeah.
if you write the sum of the poles for the self energy,
yeah,
this is number conserving. To see this, you can actually simply see that since it's the exact solution of the Dyson equation, at all frequencies, all some rules have to be respected. So not only the number of particles, all the moments, if you want, of the spectral function, so are actually exact. Now, this is if you write a sum of the poles for the self energy, but the self energy itself has to be conserving. So this is from the point of view.
I know it has to be, but in general, the approximation, it is difficult to get an approximation which conserves if it is non self-consistent.
Exactly. So this is totally correct. So look. So let's say this functional. So if you have a functional form for for the total energy from which the self energy comes as derivatives, this is actually always the case. So the self energy is number conserving if there exists a diagrammatic form in which the functional can be expressed. Okay, for this functional, there is not a diagrammatic form because this functional is GW, but only in the localized manifold. So indeed, you cannot do projection with diagrams. So okay, if your Hubbard manifold is entire crystals, it is GW, so it's actually number conserving. But if it is not, it is not number conserving for that reason. It is number conserving for another reason, and this is actually, let's say, a bit tricky to explain. But the point is that GW0, which is exactly this, in the same way, is number conserving in the point of view of Kadanoff and Boehm. Now, to see this, the simplest thing is to go to the Schindler-Meyer paper 2001 and look at the proof. But actually, the point is that this approximation to the Luttinger-Ward function or to the Klein functional, it is number conserving. Okay. But it's actually a very good point. I mean, it was a bit tricky to understand, let's say, all the details of why it is or why it should be not number conserving.
The reason of my question is that almost 50 years ago we did something similar for the hydrogen molecule. And then at the end, the number of electrons in the molecules was not 2, was 2.001, something like that. Yeah.
I see. Well, now the point is that so I couldn't do this check. So all the theory is there, but the point is that I couldn't do this check because indeed, since I have not done yet self-consistent calculations, this will come out only at self-consistency. So when I do the implementation of the self-consistent for Dyson, let's say, so when I will solve iteratively the Dyson equation, then there I can actually do the integral of the Green's function and see if the number of particles is conserved. Let's say. Okay. Yes.
Because I wonder whether what you find in the energy that is the wrong lattice constant could be due to a non-conservation of the electron number. Indeed.
So this is for sure correct because indeed the formalism is particle conserving, but since we did non-self-consistent calculation, these are not particle conserving, and indeed this is the reason why the lattice parameter is wrong.
But this could be, maybe if you renormalize by the number of electrons, this becomes correct. Or
it's possible. I did say that let's say, so since it's a very stepwise process, I want to implement the self-consistent thing and then see that this lattice parameters goes back to the correct DFT+U thing, let's say. But you're right. I mean, that can be an idea. Yes.
Okay. Thank you, Tommaso.
Thank you. Thank you.
Thank you. Giovanni?
Yes, indeed, my question is quite connected to the previous one. So
Yes.
I was also thinking about the fact that you said limitation is the fact that the method is not self-consistent, which is at the origin of the discrepancy in the equilibrium lattice constant and the
Yes.
active constants. So it is in principle possible to go beyond this limitation. And maybe did you think or try to study the effect of self-consistency in a simplified system, or a very simple case where it could be studied?
Okay, so I didn't say this, but the algorithm is actually designed to perform self-consistent calculations. So indeed, so the idea is that since we have from the point of view of the theory, it's perfect because we have a functional, which means that it's stationarized by the Dyson equation, which means that solving self-consistently the Dyson equation, you can actually get the stationary point of the Luttinger-Wald function or the Klein function, and that is a self-consistent result. Okay, so from the point of view of the implementation, so this is all fine. From the point of view of the implementation, are we safe? And the answer is absolutely yes, because since let me get the functional form of the self-energy, which is this. Since this is so this is the screen interaction is kept fixed doing the self-consistent, let's say, iterative process. So the sum over poles form of this is known. The sum over poles form of this, you can actually get it from the iteration before. So we did only the first iteration in which this G is G of Kohn-Sham. But the point is that the sum over poles is actually so Kohn-Sham was the sum over poles form, and in interacting Green's function will be a sum over poles form. So formally, this thing will not change. You just need to have more poles to deal with and to perform analytically this integral. Now, then what comes up is that, so this is will come up as a sum over poles from a formalism. The algorithmic inversion method allows you to get the sum over poles of this, of the Green's function. So this is actually can be, as I said, this is designed from self-consistency because indeed it can be iterated until self-consistency is achieved. The only problem is the number of the poles of the self-energy. So why did I not do it already, or why? Is the fact that so in Kohn-Sham, there were, so as I said, the algorithmic inversion maps the Dyson equation into a larger eigenvalue problem. Now this matrix diagonalization has to be done and has to be treatable. So I had I don't know, like 200 poles here. So this was still fine, let's say. But let's say if doing the self-consistency, you get millions of poles, then it becomes let's say it becomes difficult to perform self-consistency. But let's say in principle, it's all there.
Thank you.
Okay, thank you, Giovanni. So maybe just I have a question on this on the table. Actually, I was wondering why in the column LS and US, I don't know actually what it is, but you have two values.
Sorry.
They're quite different.
Sorry, so these are the lower satellite and the upper satellite. Sorry. So the point is that so from the formalism, of course, with DFT or DFT+U, you cannot get a satellite, but since we have the whole knowledge of the spectral function, the whole trick of this formula is that you can actually get the satellites. Now, so the satellites in the Storm-Variet are a very tricky thing because it was thought for a long time that they come from Storm-Variet was a strongly correlated material, because indeed these two can be interpreted as Hubbard bands. But the point is, and so they can only get from DFT calculations. Now this was not completely, let's say, correct, and indeed, if you do GW plus DMFT, or even if you do localized GW, they actually come up, so they cannot be Hubbard bands, but they instead come from a plasmonic, simply excitation of the U, at least in the from the localized GW perspective. Now, so these satellites are very broadened, as you can see, but if you zoom in, you can actually spot two. So if you actually zoom in on the projected density of states, and these are my two satellites, but and from the experiment, indeed, you get only these. So the point of this, why did I say all this? So the point of this is that this is very tricky to understand exactly what is the satellite. GW plus the MFT as an answer, localized GW or my work as let's say a similar answer, though the satellites are a bit more broadened. And if you do actually GW calculation that they did, I didn't put them here, they actually become even more broader. So yes, so I think that this is the full answer to the question.
Yeah, yes, indeed. Thank you very much.